Okay, the name of this presentation is called Decoding the Earth, a New Model of Tectonics, Paradigm Shift in Geology. Big one. It's by William Pagano. That's me speaking. I am a professional geologist with a master's in geology and a professional engineer with a bachelor in civil engineering. Please watch this presentation on a computer, laptop, or television and use the highest quality setting. Watching on a cell phone is not recommended. It'd be difficult to see things. Okay, there's the title again, and now it's been about 5.7 years of discoveries of truth, and I'm going to show all the discoveries I made, which are actually understated. Um, there's pretty much anything I can elaborate on because it's all related here, and that's the point. If the model's good, you'll be able to see how everything's interrelated, and I've discussed that in the previous presentations. But what I'm doing now, basically, besides presenting a summary of the discoveries, like I said, is again, it's a catch-up drawing presentation, important updated discoveries and revisions. So it's just like last time, it's an addendum, and some of the best drawings, again, are coming up, so you'll see. Okay, here is that list. William Pagano, Geologic Discoveries over the past 5.7 years or so. So I'm not going to read it. You can read it to yourself. I'm just going to scroll down very slowly. Okay, so now we're getting into the presentation of new drawings and ideas and things like that. Modifications, important stuff, important enough to go over. So what we're showing here is the current model of Rodinia. According to literature, is formed by the accretion of these different land masses and things like that. There's no real rhyme or reason to the current model, and I believe my model has a lot of rhyme and reason. It's ordered and everything, all interrelated. So what they're showing here is the Grenville Age mountain belts in orange. So I use the current model and apply it to my model, and I show the Grenville fabric in green here. And you can see there's actually a rhyme and reason here. Okay, so let me explain without getting into too much detail. But each of these subdivisions are refold structures, part of a big structure of Rodinia, which looked as such, outlined in yellow. So that's what this structure unraveled is Rodinia. You know, it doesn't have the sharp, doesn't show the sharp cone here. See where my cursor is. You can't see the legs, but I'll just explain. That's where the legs are, is the Southeast Asia zone here. That Southeast Asia refold structure here was really the legs, I'll put it that way. And all the structures or subdivisions were connected as we know Africa and South America were. So going in order, you have Russia, North America, Africa, South America, the combined land masses as a structure, Antarctica, Australia, and India here. The lost structure of continent A ended up going through the Mariana Trench, and the Southeast Asia refold structure here that connects up, remember this is unraveled, with the Russia refold structure connecting. Okay, so see this pattern here with the green. That's the what was in orange on the last on the current model. So I used that, incorporated it into my model, and this is where it would be. So you can see there's somewhat of a rhyme and reason, somewhat of a signature here. And what I think is going on is you have the long axis of the refolds is shown here, this crescent moon shape for each one of these. Okay, and then you have what I call a perpendicular element of Grenville associated fabric here in green. So it's basically on that angle to deform it as such. To make the crescent moon shape, you have the perpendicular element of the Grenville associated fabric, which is a mountain building event. And what would cause that would be an asteroid impact. So, you see this here. Now, look what I'm going to do here. I'm going to show this in black. You have it here in that more or less in that same direction, which is also along a boundary. You have it here, same thing, kind of sort of it's along a boundary. You have it here. Okay. You have it here. You have it here. And kind of sort of here. Things are distorted and unraveled and all, but you get the point. You also have some sort of bulging here. You see this green? I guess I'll put it in black here. You see where I'm outlining? Sort of a bulging. It could be like a deformation signature. You also have the fabric going, the Grenville fabric going along path of least resistance, which is like along the internal fabric, which is along, see the same shape, that crescent moon shape. So again, you have it on the boundaries. This is kind of sort of, it's sort of a mixture. You're getting the crescent moon shape in here. See South America here. And you're also kind of sort of getting that thing here. But anyway, it looks like you have it along the boundary here. So what it looks like to me is that if there was an impact causing that refolding, it would be right around here to cause this fabric to be present in those areas, the mountain building events. So that's what I think. I think there's that rhyme and reason right there. Okay? If you really look at this, you can see there is kind of a pattern there. Deformation, perpendicular element that I circled, and then along the path of least resistance, along the fabric, along the borders. All right? So I just modified this. That's why I'm bringing this up again. I just improved it a little bit. Okay, this is one of those really crazy but incredibly interesting drawings. All right, so what we got here is this drawing on the insert on the top left has been discussed before. Crazy stuff. It looks like the inner Earth outlined in red, Rodinia here outlined in yellow. Looks like this whole thing was trying to get into the center of the Earth, really. It was sensing heat or whatever, and it crashed. Crazy stuff. That's why there's that crash kind of dynamic to it. You see the yellow legs of that Rodinia structure have bent up from the impact. Weird, weird, weird. I know. There's consistencies here with these structures. I've gone over this before, just kind of highlighting how weird this stuff is. That is where this is in the insert is shown in the ellipse here, and in the featured fractals below here that I'll discuss now, they're over here. In the blue it says approximate location of featured fractals. So they're both along fault lines. Okay. So what's going on here? First of all, you can see that inner Earth shape is consistent. It's outlined in red, okay, from 1 to 2 to 3. Now that's a clockwise direction in sequence. But if you were on top, it would be a counterclockwise direction in sequence. And everything in this model, excuse me, is counterclockwise. Okay. In the insert, you can see that same shape of that inner Earth. It's got a flat section See this outlined in yellow? There's that flat section. The shape is the same. Everywhere you see, there's that flat section. Shape is the same. So once again, and the flat section is like, has the white dots on it, just so you can track where things are. So it's, in a sense, even that inner Earth is rotating clockwise from 1 to 2 to 3, but it's really counterclockwise from above. So the sequence itself, again, same thing. It's sequence from 1 to 2 to 3 is clockwise here. See my cursor moving. But if you go on top, from above, so to speak, up here where the cursor is, it would be counterclockwise. And the rotation of the Earth would be counterclockwise, which is consistent with the model. Okay, so what's going on here is Rodinia, which is outlined in white. Rodinia specifically in white. Apparently, this could be like showing a concept or whatever, or if this could be reality. But there's other refolds around, and they're outlined in blue and in green. And this green one was apparently fighting the white one, Rodinia, which won for a spot on the inner Earth, outlined in red. So what's going on here? You see number 1 here. This is the first part. It's approaching the Earth, and it does a tuck. See the tuck here? See my cursor? It's tucking down to the right, and then what happens is from 1 to 2 it flips with its rear end. You can see the rear end here on number 1 is facing towards us, and the rear end is actually facing onto the Earth on number 2. So it tucked and flipped. Okay, and it the green one was too late. He landed on top of the, it's not shown, but the cone, the top section of the white Rodinia fractal is like below, safely onto the Earth, in contact with the Earth. And apparently it pushes away at 1, because you don't see the green one in number 3, you only see the white one. So it won in the contest to get to the inner Earth first. And there it is. In number 3, the cone was released as opposed to sticking to it in number 2, apparently. And then it found its equilibrium by the cone being pushed back up here, and with all that action and everything, the legs, just like they were on the top over here, the legs have kind of curled up. See on number 3. So they will dig back in and get some anchoring on the inner Earth. As what happens is then that cone will go back around and meet up, wrap all the way around. And I've talked about this before, but you have the Russia section on the top here. See where the cursor is? And that's the Southeast Asia refold section at the bottom. So they kind of meet up as it wraps around, as that cone wraps around. And then I was just discussing in the Grenville fabric slide that I was discussing the order and everything. But this is really interesting because you have Rodinia essentially doing what it actually did. It landed with its rear end facing the Earth, and then it was by itself, and you see the Southeast Asia refold structure there at the bottom. It's going to dig in and everything stabilizes, and I've discussed this before, but this could be what really happened. So I should clarify that the green refold structure, interference refold structure that lost in the contest to the white, it also tried to land on its rear end. So in a similar manner, you see at phase 1 here, the green one coming towards the inner Earth in red, and between 1 and 2, he tucked down also, and he tried to land on the inner Earth with its rear end. That's his rear end here. See where the cursor is in number 2? Okay, so he rotated his body counterclockwise to get in that position. All that's explained in here. Okay, at the end, the green fractal's cone lands on top of the white fractal's cone below the view of the inner Earth. That's over here in number 2. and its rear faces the surface of the inner Earth after twisting its body counterclockwise between phases 1 and 2. So this guy over here in 1, the green, twisted his body counterclockwise from 1 to 2, and in the process trying to land his rear end onto the inner Earth. So you got a similar dynamic as consistency here. And just wondering if that really happened specifically, if there was this two of them fighting or whatever for the inner Earth, or if it was just Rodinia by itself. We'll never know. I mean, could be conceptual. This fractal world is really weird, as you can see. Has been explained many times. Okay, so this is the same drawing. There's just additional fractals that are shown in yellow, I believe, just the yellow. Okay. So you can see them rushing into a fault line. The fractals, as I've explained before, they go parallel or perpendicular to the fault line. And a lot of times you can see like lineations on the topography and all that. Just your standard way of mapping faults, but it's enforced by the behavior of these fractals. So you can see them kind of, there's like an agenda here. They want to get in there quick. This guy's going one way and he suddenly turns, hey, I'm going into that fault. And this guy's like floating down, like doing a free fall. All right. Yeah, so where that is again is right here. That fault in red that was shown as the black one here. So all those fractals are in the white ellipse. I'm sorry. Okay, what we got here is just a revision. This is a really cool drawing, really cool area. The one that I've shown before is this one here. So this is in Canada, Ontario, Canada. And the fractals are rushing into the fault line, shown in black. Okay. So where that is all these fractals are shown, including the new ones in the featured fractal, are shown in the white ellipse here. So there's that fault line in black below. So you can see it's pretty cool. There's some big ones there. And you see that lake Nipigon? That's right here in both. So just to see the scale here. There's some big ones on the north end, big fractals, and the smaller ones, for whatever reason, on the south end. Maybe the axis is bigger on the north end because, again, as I explained before, the fractal size kind of determines the strength of the fault or whatever. So there's like better access on this end, apparently. They're consistently smaller on the south side. So here it is. Okay. So these next slides are tons of fractals I'm going to show in Florida. And there's faults in Florida too. I mean, apparently the faults probably are not active, but they're there. And they're consistent with my model. They show, you'll see a counterclockwise rotational system. Okay, so here's the fractals. I just find this interesting. There's lots of fractals. Here's, this is pretty much central Florida. It's limestone country. You can see all the sinkholes and things. There's that fault in red. You'll see this fault on, you'll see all the faults together on one slide. That's just a close-up. I'm going to just be covering all these slides, all these drawings. So close-up here, Winter Haven, Florida, limestone country, like I said. So this is in kind of south central Florida. It looks like Orlando area, Eustis, Florida. Still limestone country. And I guess it's not far from, this is that same fault. So I show like the area in the insert. This is what I do a lot of times. So there's that same insert below. You can see right here. You'll notice there's like different types of refolds, but they're all refolds. Some are shaped more like the Rodinia type shape with the two legs and the cone. Others are more like crescent moon shaped or whatever with two little thin end legs, but not a cone. The cone was not developed in the center. So regardless, they're all refolds, and there they are trying to get into a fault, kind of getting all jammed up trying to get into the fault here. So again, I should clarify something that these refolds that are getting jammed up here, that's part of a splay system. So those are faults in themselves. You'll see that in a future slide. Okay, so there's a reason they're kind of going in like a lineation here. They're jamming up in a lineation because they're trying to follow the splays. You'll see that. So these are more fractals in northern Florida. Okay, and some nearby faults and everything and nearby fractals, which are all going to be shown on one. You'll see. Okay, this is Central Florida, basically still. There's that same drawing that you see here. And there's the splay system to the north, okay, in white. And it also goes to blue here. See the cursor. So there's fractals demonstrating that splay system. Okay, so you'll see all these together, like I said, on a drawing coming up. Okay, here is the fault system with plenty of fractals demonstrating some of the faults. Okay, so in my model, 105 to 110 million years ago, I was showing Florida with a pretty rapid high energy event where it was rotating counterclockwise. It went from the red to the yellow. So you see that counterclockwise rotation there 105 to 110 million years ago. Okay, so I think that's how old these faults are. We've seen these inserts before. So if you look here, the age of these faults are the following. It's a counterclockwise system. And you have this red one, then the blue. See, I'm going counterclockwise. Then the white, then the splays on the white in that direction from right to left. Well, it could be happening simultaneously with the blue, but basically the blue is advancing counterclockwise from the blue and the white here. So this second blue, where the cursor is the next one. And then the one after that is the green. Okay, so you can see that signature counterclockwise motion there. Okay, this magenta fault here, I guess is more recent. I was saying it's tied into the shape of Florida more. And you see these curved sections here. These are faults that are verified by fractals. I think there's probably still counterclockwise rotation, a little bit of sliding as such. See the cursor probably lands like kind of separating as such in a counterclockwise motion. It's like slicing off, kind of. That's what I'm saying, or it will eventually along these weak spots. So this is basically the same drawing minus the fractals in the featured drawing here. So it's just cleaned up. You can see things more clearly. Oh, and something very interesting here. I pointed out this dotted yellow line. Dotted yellow line is a lineation that mimics the shape of Florida together with the southern part of the magenta fault line. So this forms like the shape of Florida. There's between this fault in magenta and this lineation in yellow. See the shape of Florida? It's mimicking it. That's like a true fractal, the fractal definition. Note the miniature Everglades at the south end. Okay, so at the south end of Florida, you have the Everglades. All right, and you have like a little notch in the Everglades. See that? There's like a notch here. So the Everglades has a notch that's at the south. In this miniature Florida. Well, now let's look at the big Florida. There's the Everglades in the south. And what's the notch? The actual lake that shows another notch in it. So that's like a true fractal there. That's like you're looking at systems here. Let me highlight it just to be clear. So you have like a notch here, and you got your lake at the south end of the fractal of Florida, basically. Okay, and then again, the notch itself is the lake here, and there's your the swamp, the Everglades itself, like that. Okay, so this is your swamp and this is your lake. So on this is your lake and this is your swamp. That's like a true fractal. This weird stuff to the right, I guess that's fractals. I'm calling them fractals. But a true fractal is what I just showed you. Okay, jumping into another thing here. This is the East Coast subdivision of the North America subdivision refold. All refolds. This is just a smaller subdivision of the North America refold on the Northeast. So that's what's outlined in blue. There's the dynamic of the land snapping between New Brunswick, Canada, and what is now Alaska area. The arm snapped. This went down, made some compression features in blue as it snapped, and it's now rebounding back to the northeast. I've explained this before, and some of the proof is shown in these inserts. I've discussed this all before. Okay, but as a product of all this dynamic I explained, there's the brittle on the surface, Brevard fault zone in magenta here. It's right lateral movement, so if you stand on either side of the fault, the movement is to the right. And I believe it's related to ductile rebound movement to the northeast. I was talking about that rebound. It snapped down to the south and west. Compression features were made. Now it's rebounding back to the northeast. And actually, you can see it in the phases. It went from yellow, this rubber band, the snapped rubber band, so to speak, went from yellow to red. And the brittle breaking is along that magenta fault there, the Brevard fault zone. So product of that, if you think about it, that movement from yellow to red is more shown over here. See the cursor? From yellow to red is right lateral. If you're standing here, you see it moving to the right. So I guess that's more dominant than this part where it moves from the yellow to the red, because then it would be left lateral there, but instead it's right lateral, so that the movement, I mean, you could, in reality, you could have like no movement here and really just movement here. But the end product is that the result is stronger movement on this side from here to here, from this yellow to the red, and it's expressed in the fault in magenta. It's the right lateral fault. Okay, this drawing is just, I just added this fractal here in the north here. This is in Canada, and there's a pretty cool one there that I just added in, outlined it in blue. And check out the diversity of the shapes here and the angles and everything. Really interesting stuff. Okay, this is the Northeast North America, Northeast United States, really. So the blue faults are a system of counterclockwise movement. You can see I've gone over this before also. The yellow faults are related to Boudin path phases. I've gone over the complex dynamic here, how age progression is from right to left is the most recent. So the oldest is to the right. So that's why there's that dragging. So where the cursor is, a dragging in the yellow phases on the right. Anyway, purpose of this drawing is to see the relationship between the Newark Basin here, see the cursor, and the Hartford Basin here. Two big basins in the Northeast, Eastern America, North America and all. So I think it's related to this fault system. See the arrows, there's a right lateral movement and counterclockwise system, like I said. So it needs more investigation, but I think that, this is the link between the fault system and what we actually have. So there's a reason for it. You can see it here. So, okay, now we're changing gears again, but it's all related. It's all a counterclockwise thing going on here. So this is a fault system, and propagation is counterclockwise. It's a system of faults in eastern Pennsylvania, New Jersey, lower New York, metropolitan area, New York City. This took a long time to do, and there's like a zillion of these fractals. You probably want to check out the PDF, zoom in and out. It's pretty wild stuff. Um, Newark Basin is, you can see the magenta fault in the Hudson River here. You see the cursor. Okay, it comes down, goes by Manhattan here. See where the cursor is. Comes down. And it goes through Staten Island. Okay, and I just drew different colors. I actually matched the colors here in this published map here. I put in here. So everything confirmed. The fractals, by the way, confirm these faults. And of course I drew like a zillion other ones from the fractal behavior. Okay, we're going to talk about this section here more coming up. It's rotational zone. You got plenty of rotational zones in here, you see, that are ready to get worse or whatever. There's another. Okay. I think that different faults all join into this magenta fault that I was just showing. See these faults here, this whole system comes into the Hudson River, and then it, or the magenta fault, at least I'll put it that way, and then it like splits off. So everything joins up at certain points and then splits off. And the system, as I was saying, fault system movement and propagation is counterclockwise. So the system movement goes in a counterclockwise direction. Okay, for example, for this counterclockwise rotation. So see the white fault here? See the cursor moving? I'm pretty sure I went from the white fault to the green fault, counterclockwise, to the yellow fault, at least here. I'm not sure if it went to the red fault here and then the green, because I know that, or I would suspect that in the Newark Basin, which is up here, see the cursor moving around, I think the propagation goes from this reddish pink fault here to the blue, to the red, to the magenta, to the yellow, because it's propagating up as the rotation, see the cursor is in a counterclockwise direction, which so it's like arched. See, it's arched here. There's compressional features in the Newark Basin. I wonder if that's from the when that rubber band snapped, so to speak, and everything came compressing as it snapped down to the southwest. Now it's rebounding to the northeast, and motion is in a counterclockwise direction. So there's like overprinting of different things going on. But I think, again, that counterclockwise motion propagation is what I was just saying in the Newark Basin, which is in the center reaches of this drawing, the Newark Basin. And here, it's not clear to me, but I'm pretty sure I can say with confidence that it goes from the white fault to the green to the yellow. Then I'm not so sure. Maybe you have like a little zone in here that propagates from this magenta, see the cursor, to the green, to the red. Or is it from white to green to yellow to red? There's questions here, but there's definitely a fault system propagation movement, and propagation is counterclockwise. So you could even see in the splays, all these splays, they're arched in such a way where the motion is counterclockwise. See that? Everything is hooked, developed in a counterclockwise direction. All right, that's what I'm saying. If you take a look at it, it all makes sense. You have like drag folds here because the movement is this direction. It's going to snap one day because it's sticking there. You can see it kind of arched. All right. What else could I say? You have brittle, which is this red fault here on the published map. And this red fault that's more straight right here, that's the brittle fault. I think it's confirmed by the fractals and all, but there's also a ductile fault here in the dashed. I said deeper ductile fault splay maybe at the dashed line here. And it's on the edge of a big white fractal here. So I think that's the ductile one. Has a nice arc to it, just like the others, very consistent. You know, it's just another splay. Okay. So I suggest checking this out sometime. There's really neat things going on with some of these fractals too. See what's going on here? There's a white one, see the cursor, then the blue and the red and the white here and the green, they're all kind of rushing into this one spot here. So it's like, I guess that spot is pretty open or whatever. That's why they all want to get in there. Yeah, so there's so much going on here. It's hard to even get to everything, but wanted to show this, and I suggest, like I said, you look at it on your own. Okay, here's a close-up of that section that's rotating. There's a rotational zone here. We had an earthquake in New Jersey at 4.8, and that's the location of that epicenter is the blue dot here. I'm circling. And then there's a whole slew of aftershocks afterwards, and they're shown, I think they're all shown, like there's no earthquakes that are not aftershocks that are shown here, except like a few of them from like 2011 or something in this area where my cursor is now. But I'm going to get more into detail into this on the next slides. I just wanted to show the fractals overprinted on the rotational zone here. There's also a map of published map of the Round Valley faulting, the brittle faulting in that area. This is showing the rotational zone. You see it's pretty much circular, and based on where the earthquake and the aftershocks are, which is in the white ellipse, they're all inside there. It's kind of interesting. Makes a nice white ellipse here, and there's only like 2 other earthquakes aftershocks here, and this other little tiny white ellipse here. But you can see the rotational zone is there for a reason. I'll explain more in the next slide. Okay, I want to address more detail in this. Let's read these text boxes. I want to define what we have here. The white elliptical zones are clusters of 2024 earthquakes within the circular rotational zone, which is shown in black. So this is only the aftershocks, and the one in blue is the main earthquake, 4.8. So you see the nice white big ellipse here, and the tiny one over here. Okay, all encompassed in the black rotational zone. What we have here, the faults, let me describe what they are. Mapped faults, like published literature, are solid red. We talked about this one here. See the cursor? Solid red. Solid yellow. Here. Solid yellow. Okay. And solid blue. Right here. That's from that published map. Solid green and all dashed lines are unmapped faults determined by fractal behavior. That's from my model. So the solid green and all dashed faults. Okay? So what I think here, based on these fractals, first of all, I swung back the gate to where it was. The gate, so to speak, is this one here. See the cursor? It swung open, but if you put it back where it was, it's right here. And you have fractals confirming that. So that's where it was, and I think the ductile one was here, and the dashed red, see the cursor again. So in reality, maybe the deeper one goes here in the red and yellow, and the brittle one on the surface was once right here where it actually broke in a brittle way. And that's what swung open, so to speak, this gate in a counterclockwise direction. Okay. So the ones that are mapped out based on the fractals, like this dashed blue one here, all in this rotational zone. And these green ones, these are unmapped that I put in because of the fractal behavior here. You can see the fractals going into them. They're always parallel or perpendicular to faults. So I drew them in. Just for comparison, there's a brittle map overlay of Round Valley Reservoir here, published map. And just looking at the difference here. See this brittle one, for example, the cursor right here. It's a brittle fault. It's probably related to this green one that I mapped or confirmed, depending on how you look at it. That comes this way. I think this has to do with sort of the bulldozing effect, in a sense, of this rotational zone. So that gate swings open, things are rotating in this zone counterclockwise. And it sort of pushes up to a front and then kind of grinds on the front. That's what I think the green represents. And I think it goes from this one, see the cursor, to this one, because that's a counterclockwise direction. It's pushing this way, and then it's, let me see if that's right. Yeah, you have this one, and then it advances further down as things propagate more. So you have this one first, right here, and then this one as things kind of propagate more. See the arrows of the yellow arrows coming down as it advances more. It goes from this to this, which is a counterclockwise direction. Okay, so back to what I was saying here. Weak zones along counterclockwise rotational zone as discussed below, right? The zone also borders the green fault line. So you're going to have a rotational zone where it's allowed to slip. And there's tons of rivers in here that I put in blue. These are the bigger rivers in the area. The weak spots on the faults are going to tend to be at the kinks and along the rivers and stuff. Okay, so there's actually a whole bunch of, the upper Rockaway Creek comes together, a whole bunch of streams join up right where the cursor is on the northern part of this kink area. So that comes in, and that's a weak spot, that's a kink. That's probably why the branches came in, lots of activity with streams in that area. And then as you come along here, you see you have the fault, and of course along faults you tend to have rivers. So these are the bigger rivers in the area, shown in blue. You have an intersection here, two rivers, Lamington and the North Branch, and you have more rivers up here. You can see the action that things get pulled along a fault too. The stream kind of gets pulled along the fault. That's evident there. It likes to sort of spend its path in there as much as it can. That's probably why it loops around in here. Okay, so what I think is going on, looking at the big picture, I think you have a lot of activity on the back end of this rotation, and it's sort of pushing along till you get a frontier. It's not going anywhere, but I think it will once it is allowed to lubricate this fault line system. Once this is allowed to move, I think the whole thing's going to spread and rotate. It's going to mobilize, and it's going to swing that gate open. You know, once this front end is allowed to mobilize, then that gate's going to swing open, this yellow gate here, and then what's going to happen, you know, one of those catastrophic events, all the broken, brittle sort of shards of glass on the north side of the fault, of the border fault. You have the highlands, the older rock here. You have the Piedmont to the southeast here. So anyway, I think a lot of those pieces are going to like kind of get shifted around and sort of get through the gate a little bit, or try to push through the gate. As the really what's going on is the whole system is rebounding to the northeast, as I was saying before. So that's what's causing all this rotation, this counterclockwise rotation. Okay, so I said something that's not really true. I said that, see this faded yellow line here, that's the initial position of the gate, so to speak, before it swung open. This is the brittle fault, and I pushed it back to its likely starting position just to see how it looks. The fractals do not confirm that, actually. If you look at them carefully, the fractals do confirm the deeper ductal fault here that I put in red dashed line with yellow dots. So that's really confirmed heavily by the fractals. Okay. So I'm sure they're related. I think that is, in fact, a deeper ductal fault, and that's what this is all about. That's what these fractals show. They show the... they also show brittle sometimes, too, or in between brittle and ductal, but it seems like they're showing the deeper kind of ductal plastic faults. So I think that's what's going on here. Got to think about why it's not confirmed by any faults Um, why that is, I'm not sure. I don't have to do if it has to do with timing or how strong the fault is, but it's definitely confirmed at the deeper levels, where it's like right here where the cursor is, where that is drawn in the red dashed line with the yellow dots. Okay, we've seen this map before. This is the the system that includes some published information, some published mapped faults here, and it has my system that I determined by all these massive amounts of fractals. So based on the fractals behavior, I mapped it out, this system here. And what I wanted to show was, you see this fault here. This is a mapped fault. Of course, I went outside the boundary a little bit, but this is what's called, it's really two faults, but it's Huntington Valley, Cream Valley faults in the central and southern region, definitely the southern. Cameron's Line mapped brittle fault in the northern region, traced in yellow with black dots from overlay source here. Okay, so I wanted to see how close it is to the faults that I put in, and it's a mixed bag. You'll see here. The mapped brittle fault described to the left does not align well with fractals at its southern end, shown in this figure, but the adjacent ductile fault in yellow does. Of course, that's why I mapped it, so because it's based on fractal behavior. In the central and northern ends, it appears to be related to the adjacent ductile faults, although it crosses into the Newark Basin in plan view. So you look here, it's not confirmed by the fractals. See the dotted yellow line, whereas mine is, of course, because that's how I developed it. But I'm sure it's related. Okay, so the brittle breaking is different than the ductile system or whatever. And then it joins up, and it's the same thing in the center regions here. See that? My fault joins in here, and it is right along the published map here. And all the fractals, of course, are going into it parallel or perpendicular, except for the big ones, remember? Okay, so it comes along. Then it's really Cameron's Line fault as you get up in the New York metropolitan area. Here it's crossing into the Newark Basin. Newark Basin is bordered by this magenta fault here. See the cursor? So it goes into it, which is possible because at depth is one thing and at the surface is another. So this data in general is going to help me determine basically how deep these ductile faults are, like that are confirmed by the fractals. I can get an approximate depth if I know structural data for the brittle faults at the surface, these mapped published faults, and with like the dotted line here. Okay, so here it is, New York metropolitan area, not confirmed at all by these fractals, but I have a system of faults nearby. I'm sure it's related. Okay. So I should take a better look at this one day and get some more information on what my model's telling me with these fractals. How deep are they? What's going on and all that, because there's brittle versus ductile behavior here to compare. Okay, this is the gigantic fault system in Europe and Asia. Southeast Asia, refault structures here on the east side and all. I've talked about this dude in red, this fractal in red, showing a lot of strain and all that. But I didn't realize there's a fault right here. So I added this fault in blue. Just for completion, it's interesting because that explains why this guy is under strain. He's trying to he's too big to get into the fault, I guess. So he's going parallel to it and he's under a lot of strain, which is really weird. Like, why do these fractals show strain and bending and it's just so bizarre. It defies science as we know it. So I should clarify that I drew this blue fault in here by digging into things more, published map and stuff. And what you got here is apparently this fault that I drew in blue is this AL SSC fault. So I put that in, and it matches perfectly with this guy in red that's under strain trying to get parallel to the fault because you can't get into it. And see the other one's all, apparently it's a pretty powerful fault because this guy in yellow too, he's associated with it. Right? And strange thing is, why does the green one go right through it? I'm not sure, but it's definitely controlling this yellow one and the red one. Okay, I'm saving the best for last. This is really interesting. Okay, so you've seen this map before, this drawing, I should say, without those green uh, LLSVPs. I'll get to that in a minute. So this shows the history, those arrows show the history of movement up to about 35 million years ago. And it's pretty similar to today. There's only tiny modifications to today. And actually, I wonder if I even included them. But this shows it the best up to that point, 35 million years ago. So what it's really showing is an expanding Earth, essentially. I know it's very controversial, but it really, really looks like it. I mean, I put in blue, tension zone in blue. This is confirmed by geologic literature and mid-oceanic ridges and everything. So kind of surrounds Africa, tension zone. So that means expanding, pulling apart. And it looks like you have basically a triple junction. So I'm going to put it in red here. You have one arm here, one arm here, and one arm here. Okay. I didn't draw it exactly, but anyway. I thought it would be thicker, by the way. Maybe I got to do like a 10. So that's your triple junction. Sum of the forces in this direction equals the sum of the forces in that direction. Sum of the forces in this direction equals the sum of the forces in that direction. So you have this and that. So it's like your triple junction. It's like a mud crack. You have when mud dries out, it forms a triple junction like that. It's expanded, and then it contracts when it dries. So it makes a mud crack. Anyway, so these LLSVs are called large low shear velocity provinces. The LLSV trends appear to be consistent with global expansion of the system of land masses. So the system is under tension. There's localized compression, such as at some of these trenches. And what happens is like this continent A here, this is the whole thing that I talked about. When that went into the earth basically and formed the shape of the Mariana Trench here, we're sort of in a time warp, so there's like still subduction there. So it's localized. Any way you look at it, it's localized compression in a tensional system. Everything's under tension here. It's pulling apart. And I think these green LLSV zones are associated with it because it's kind of pulling in the direction of the growth. The growth is in the direction this way and that way. So things are pulling that way. This is kind of, there's no LLSVPs here, but that's just rotated off that way. Regardless, it's growing in this direction. Okay, so this tensional system is being pulled. And remember, this is unfolded, so to speak. If you put this into a globe, it's, what you got here. And I simplified this published geologic literature with the simplified version of what you see here in the green. So it's definitely an expanding Earth with localized compression.